And I'd like to invite our first speaker up, Markus Nordlund from PMI Science.
Thank you so much for the introduction. Now we see where the slides are. There we go. There we go. So it's a pleasure to be here. I'm Markus Nordlund. I'm the Global Head of Strategic Scientific Initiatives at Philip Morris International. And today I'm going to talk about everyone's, I'm sure, his favorite topic at school, which is physics and chemistry, right? Everyone is delighted to hear about it. I will actually talk about absence of combustion and smoke, and why that is important for heated tobacco product in particular, but also for tobacco harm reduction as a broader concept. And also to show more specifically of how can one ensure that the products that we actually do develop actually does not have combustion and that the aerosol generated is not smoke. To do so, I'm going to first introduce a little bit about what is heated tobacco product. I'm sure most of you are aware of it, but just that we are on the same page. And then to also talk about how to substantiate it from a chemical and physical perspective. What are the attributes that we can use from a physical chemical perspective to actually check whether or not you have combustion and smoke in a product? And then go more into some examples of what we do for our technologies, heated tobacco technologies, to substantiate these features, and then conclude the talk after that. So if we start with heated tobacco products, it's actually products containing a tobacco substrate that is designed to be heated and not combusted to generate a nicotine-containing aerosol that is not smoke. This is what heated tobacco products are in general. And of course, there are many, many different types of technologies one can use to heat tobacco without combusting it. And I'm going to go through just very briefly two of our technologies that we have at Philip Morris for our products that we have commercialized in the markets. The first technology is based, it's actually the one that is in the commercial version of IQOS with heats, which is based on resistive heating. So basically how it works is that you have a heater, you can actually see outside in the booth after, PMI Science booth, where you have the device that actually heats a tobacco stick. So insert a tobacco stick over a heating blade that is part of the device. This heating blade, as you can see here, is actually a ceramic blade, but it has a platinum track that actually provides the heat to this heater blade to be able to heat tobacco from the inside of the tobacco plug on the tobacco stick to generate the vapors that then comes in form of an aerosol to the consumer. Now the beautiful thing with the platinum track is that it actually acts as a temperature sensor at the same time as when it actually produces the heat, which makes that you can control the temperature directly by this technology. And this is, of course, fundamental to be able to ensure that we do not get combustion, because you really need to control the temperature to not get an uncontrolled situation. Now, the second technology that we have in our most evolved tobacco heating system, which is commercialized as IQOS Illuma with Terea in some markets, is based on a slightly different heating technology, but based on the similar principles in many ways. So it's still heating tobacco from the inside of the tobacco plug, but it uses induction heating. So basically how that works is that you have a coil module which creates a magnetic field that transfers energy to a susceptor which is actually integrated in the tobacco stick, like what you see here actually. So you have the coil module, transfer it, so in each tobacco stick you would actually have effectively the heater part of it. And of course, this technology is also important to control the temperature, and this is done indirectly by the conductance, the magnetic conductance of this system together in the tobacco stick. And this is how you can actually control also the temperature profile that you actually have when you use these type of products. And of course, there are other technologies as well in general that you can have, but these are the ones that we have in our commercialized products. So now the question comes, so how can you substantiate that you do not have any combustion and smoke in our products, or in heated tobacco products in general? Well, this is based on physics and chemistry, right? It's no hand-waving. Mother Nature tells us that when you have combustion, you must have 3 different components, otherwise you just cannot have it. You need to have a fuel, so tobacco in this case then, oxygen, which is in the air, you cannot do much about it, it's there, and you need to have enough heat to ignite the tobacco. So you need to actually kickstart the reaction by providing heat, and it can only happen in an oxidative atmosphere. So combustion is actually rapid oxidation reactions generating heat. So this reaction that happens after ignition actually kickstarts a reaction that generates more heat than what it takes to actually start the reaction. And that is why it goes on by itself, like in a cigarette. You know, you light it, and then it goes on because it generates more heat than what it actually is consuming. And then when you do that, you actually leave ash behind. So whatever that cannot be combusted is actually the ash, which is gray. I think you all know that from the cigarettes, right, what you see. And you get smoke when you have combustion. Now, if you look at the smoke formation, you actually have a smoke contains solid and liquid particles in a mixture of gases in them that are generated from chemical reactions or byproducts of chemical reactions that occur at a high temperature associated with tobacco combustion. So these solid particles, like soot particles, for example, are generated when typically aromatic hydrocarbons, etc., some group of compounds that typically come at high temperatures, and they go together to form these solid particles. In cigarette smoke, for example, you can see that you have more than billions of carbon-based solid particles, but also more than 6,000 chemicals that are actually emitted during combustion. And out of these, roughly 100 or so has been recognized as harmful and potentially harmful by public health authorities. Now, even though smoke is an aerosol, it's very important to realize that all aerosols are not smoke. Even if it's look white and cloudy, doesn't mean that everything is smoke. That's what you see that has this form. Look at e-vapor, etc. And the difference here is really how the smoke particulate matter are formed, because in smoke, as I said, is the byproducts of chemical reactions. You need to have a certain temperature and generate a certain amount of compounds to actually get to smoke particle formation. Whereas you can also generate aerosol droplets by vaporization and condensation, which is a physical phase change process, and no chemical reactions there. And this is, of course, very different. So if you look at the combustion principles and the smoke formation, you actually have clear indication of what attributes you need to have to substantiate absence of combustion and smoke in heated tobacco products. So the first thing is to ensure that the tobacco temperature is below ignition. If you do not ignite anything, nothing will combust, just Mother Nature, okay? Since combustion is an exothermic, so heat-generating process, if you see signs that you do not have heat generated, it's also a very good indication that you actually do not have combustion. Also, since combustion is an oxidation, rapid oxidation reaction, if you can actually show that the emissions that you have for typical compounds are equivalent in a nitrogen atmosphere where it's impossible to have combustion compared to in air where you can have combustion, you can actually see that you do not have combustion in the product if those are equivalent. In terms of smoke, you can also see, since smoke contains solid particles, carbon-based solid particles, if you can actually demonstrate that the aerosol generated by this physical phase change process in heated tobacco products are actually liquid-based without the generation of solid particles, also good evidence that it's actually not smoke generated. Of course, you can look at ash as well, see if you have ash spots in the tobacco after use. And something that is often used in the combustion science is actually looking at the ratio between carbon monoxide and carbon dioxide. Low ratios in this actually indicates that oxygen diffusion is not a prominent feature and that you do not have a combustion reaction, where this one would actually go up very high. And also, of course, all this sums up to a reduction in what we are interested in terms of tobacco harm reduction as well, in the reduced emission levels of harmful and potentially harmful constituents. So now I'm going to show you a little bit like how this looks like for some of our technologies for the tobacco heating system. So if we start at the temperature, tobacco that is used in our tobacco products, heated tobacco products, is actually based on cast leaf tobacco. We have seen that the ignition temperature of this tobacco is around 400 degrees or so. And the maximum temperature that we measure in this product by using thermocouples, basically a metal wire that you put in and you try to measure the temperature at the hottest spot, it's actually 320 degrees as maximum, which is far beyond, below the onset of ignition and combustion. And something that is interesting as well, because you remember it's an exothermic reaction combustion. Like everyone, I think, knows when you have a cigarette and you puff on it, you see that it glows, right? Because you have more oxygen coming in, combustion reaction gets all violent, and you see that you get this temperature peak, it goes up. What happens here, though, in heated tobacco products, since you do not have combustion, you can see that every time you take a puff, which is basically dipped, it goes down. So you basically just cool down your tobacco. Even though you have more oxygen available when you puff, it cools down, which shows that you do not have any heat generated at all during use of these products. Also, if you look at the emission levels, we did experiments in air and in nitrogen on our tobacco heating system. And if you look at carbon dioxide and carbon monoxide values, for example, the first thing that you see is that they are significantly lower compared to what you have in combusted cigarettes, right? These are the products in air and in nitrogen. But also that they are substantially equivalent between the two atmospheres. If you think about if you have a cigarette that you light compared to a cigarette that you do not light, if you puff on them, it will be hugely different in the nitrogen atmosphere and in air, because you actually don't get oxygen to combust. So the fact that they are substantially equivalent and very low is a good evidence that they actually do not have a combustion process happening. Also, when we look at the presence or absence of solid particles in the aerosol or collected aerosol from the tobacco heating system, compared to the smoke that you get from a research cigarette, you can actually see that this is actually, you pass it through a thermodenuter. It's not so important what that is. You basically vaporize everything that is volatile, and you try to collect to see if there are some solid fractions left in the aerosol. And what you see is that for the tobacco heating system, it's equivalent to your blank sample. You basically do not see any generation of these carbon-based solid particles, whereas if you do the same exercise for smoke from a combusted cigarette, you'll see billions of solid particles actually collected on the plate. And of course, in terms of tobacco harm reduction, I guess I don't need to elaborate about the importance of not having solid particles. I think to be inhaled there as well. Then, of course, if you also look at, do we have ash or not? So if you actually open up the tobacco stick after use, you can actually see that the only thing that happens, maybe it's a bit difficult to see on the picture here, is that you just get this darkening, blackening of your tobacco in the close vicinity of the heating blade. And this is the same process that happens when you cook food, right? If you have a plant-based materials, your vegetables, and you actually heat them up, they do change color and to become like darker. It's the same process, and it doesn't require oxygen. It happens the same thing in a nitrogen atmosphere. So the fact that you do not see these gray spots of ash is also very strong evidence that you actually never had any combustion process occurring in the tobacco. Now if you go to the carbon monoxide, carbon dioxide ratio, in cigarettes, if you look per puff and you collect and you calculate this ratio, the typical values above far beyond even 20% is typically seen, 30, 40%, depending on the product. And this actually shows these low values that you hear, under 8% or so per puff, actually indicates that you do not have any oxygen-driven process like combustion, because you see a clear jump, like from a physics point of view, when you actually have combustion in this ratio. And finally, if you look at the emission levels that you have in terms of harmful and potentially harmful constituents, if you look at the priority list, for example, from FDA, WHO, IARC, and the average reductions when you do not have combustion, if you look in the product that's been assessed here, it's around 95-ish% or so on average. Which of course is because you do not have these high temperature processes that occur at tobacco combustion. You know, when you have combustion, the fact that you generate heat, it increases the temperature. And of course, when you increase the temperature, the more violent reaction gets, and you create a lot of compounds. And this is actually a sign that you actually keep at low temperatures and that you do not have a combustion process going on. So then, to conclude, you can actually see that based on physics and chemistry, your favorite topic at school, I'm sure, you can actually make sure that you have a substantiation that is scientifically based to whether or not you have combustion or whether or not your aerosol generated is smoke. And I think it's very important and something that we do very diligently at Philip Morris to actually assess our products to ensure that we have a non-combusted smoke-free product for this. So with that, I would like to thank everyone for the time to present to you and for that you kindly listened to me, and I'm happy to answer any questions that you might have on your mind.
Thank you very much. Are there any questions? Say who you are, where you're from. Thank you. So there's a microphone should be coming to you. Indeed, there's two.
Thanks. Hi, I'm John Oyston. I'm a retired anesthesiologist from Toronto. I'm puzzled. Doesn't the presence of carbon dioxide at all signify there's combustion? I don't know where the carbon dioxide comes from if you don't have something burning.
So this is quite an important misconception that a lot of people have. They think like, oh, you have some levels of carbon monoxide. As you see in the data, maybe I don't know if you actually saw it, even in nitrogen atmosphere, you would get low levels of carbon monoxide. And the reason for that is that when tobacco breaks down when you heat it, during pyrolysis processes, you actually generate low levels of carbon monoxide and carbon dioxide coming from when, for example, the tobacco components, hemicellulose, cellulose, pectin, lignin breaks down, and you get low levels of these compounds. What you get when you have combustion is a huge amount of these compounds. So just because you have some of them doesn't mean, I even get it when I breathe out now, I have carbon monoxide, but I hope I'm not burning. So I think it's really looking where it comes from. So it's not just one-off in terms of emissions. You really see a threshold jump when you have combustion.
Any other questions? No, can't see. Well, thank you very much. What I can say, while Markus is here, is you can get more of Markus via the GFN 5s. So this gives me an opportunity to promote the GFN 5s. If you look in the conference program, there's a list of when you can either watch them live, scheduled, or after the event, you can get them via the web. But Markus, thank you very much.
Thanks so much, everyone.